and welcome to section 3.8. We're going to talk about percent composition of compounds, and we've already seen percentages before in that if we were looking at nitrogen and oxygen, we're looking at a 1-to-2 ratio between nitrogen and oxygen and nitrogen dioxide, where it's a 1-to-1 ratio in nitrogen monoxide. So here's the structure of nitrogen dioxide, and we'll see that there is a double covalent bond. And so they're actually sharing 4 electrons between the nitrogen, which is the blue atom, and oxygen, which is the red atom. Whereas on the left-hand side, there's a single bond. And so there's only sharing a pair of electrons to the other oxygen. Now, in a mass percentage, as we've seen before, it is the mass of the entire compound on the bottom and the mass of the element in the compound on the top, or part over whole. And so we're looking at part of the molecule over how much does the entire molecule weigh times 100. Okay, so this percentage should not be on there. And so we'll see that in a compound that has Fe2O3, which is the common iron 3 oxide, which is common rust, we'll see that it is 69.94%, and we have to say in terms of what chemical behind the percentage in iron. So what does the entire molecule weigh over how much does all of the iron weigh? And there's 2 irons in this compound. So if we were looking at nitrogen dioxide and we were asking what is the weight percent of nitrogen and oxygen given the molar masses of all of the parts of it, here we could calculate what is the molar mass of nitrogen dioxide. Okay, and so this must be a typo up here. And let me put that in my textbook because I just noticed that just now, and it's weird how I can notice stuff like that, but not while I'm typing it. And then how much nitrogen is in there? Just 1. And so times the 100, and we're going to get 30.4% of just nitrogen by weight. We could do the same thing with oxygen. There are 2 oxygens in NO2. The entire molecule weighs 46 grams. Okay, and we'll get 69.6% in terms of oxygen. And we do want to state in terms of oxygen and in terms of the nitrogen. Now we could go on and ask what is the percentage by weight of nitrogen and oxygen and nitrogen monoxide. Now, here it says morphine is derived from opium plants. Okay, it's a painkiller. It's highly abused, highly, what is the word? Can't even think about it. It's definitely a drug in which someone can get hooked on it and addicted to it. The formula is C17H19NO3. And it says, what percent by mass is carbon in this compound? And so if we wanted to look at how much carbon there's 17 carbons. Okay, and so we're going to have 17 times the mass of carbon from our periodic table, 12.011. Over the entire molecule's mass. Okay, and so if we were to determine that, we would have the 17 carbons plus the 19 hydrogens plus a nitrogen plus 3 oxygens. So we would find all their masses on the periodic table and add them up and multiply it by 100. And if we did that, we would come out with the 71.559% in carbon, what I have right here. Now, we've already seen this in previous chapter, in chapter 2, in terms of percentages. But now we're going to look at these percentages and be able to do something with those. So here it's another problem. What is the mass of hydrogen percent in 1 mole of water? And what is the oxygen percent? I'm just going to go through that very quickly here. So if you need to slow down the video, you can. But here we have the mass of hydrogen in 1 mole of water, what is the mass of oxygen, and then here are the mass percentages for both the hydrogen and the oxygen. Now, if you get the mass percent of one of the chemicals, and there's only one other element in the compound, you can just take 100 and minus the percentage of the hydrogen here in order to get the percentage left over for the oxygen, because it's the only other element that's present. So it's very fast and easy to do that instead of finding the mass of the oxygen and dividing it by the total mass of the compound. Because there's only 2 elements in this compound, we can just take 100 minus the mass percent of the other element. Now, this mass percent then is going to help us determine what are called empirical formulas. Up till now, we've been looking at molecular formulas. It's a written formula that will actually tell us the actual number of atoms of each type of each element in a molecule. Now, N2O4 is a molecular formula. It tells us for every 2 nitrogens, seen here in the gray atoms, are present for every 4 oxygen atoms, present here as the red atoms. The empirical formula of N2O4, though, is showing us the simplest whole number ratio between the elements. So this, in this case, would be NO2. Because if we're looking at the molecular formula, this is not the simplest whole number ratio. You can still reduce the subscripts, but it has to be a whole number. And so we can divide them both by 2 and get NO2. So this is the empirical formula for dinitrogen tetroxide, the actual molecule. Now, up here, the mole-to-mole relationship is going to be 2 to 4, or as we see, 1 to 2. And the molar ratio, whoops, let's go back here. I don't know why it doesn't want to go back. Interesting. Is also 1 to 2. So an empirical formula is the simplest whole number ratio. For example, we have CH here, a 1-to-1 ratio. The empirical formula is an integer multiplied by, the molecular formula is the empirical formula multiplied by some integer n. And so if we were to look at C6H6, which is benzene, this is the actual formula of a real compound in life. Its empirical formula, though, it's a 1-to-1 ratio between carbon and hydrogen in the actual molecule. But the empirical formula also shows us that simplest whole number ratio. And if we were to take 6 times that empirical formula, we would get the actual formula of the compound. Now, this is going to become important when we're analyzing new compounds, because we can find the empirical formula in the lab. And then from the empirical formula, we can determine the molecular formula of the actual molecule. And so using these 2 pieces of information, we can start to identify what the formula of the actual new, brand new, super secret compound that we just made. So here, if we had a table, we should be able to fill this in and tell us what the molecular formula is given an empirical formula. Now, the molar mass of the actual molecule weighs 26, whereas the empirical formula, if we were to just look at it quickly, carbon we know weighs roughly 12 and hydrogen weighs 1. So the empirical formula weighs actually 13 grams per mole. The actual molecule is twice as big, because if you took the 26 grams per mole that the molecule is supposed to weigh and divide it by the empirical formula mass, you're going to get a factor of 2. And so you're supposed to multiply this empirical formula by 2 to get the molecular formula, C2H2. Here, CHO, but the actual molecule weighs 116. So we have 12, 1, and 16. So we have 17 and 12, which weighs 29. And so if we were to look at this, this is 4 times as big, or C4H4O4. Now here is the molecular formula. Let's try to find the empirical formula. You'll see we need to reduce this. If we were to divide each of these by 8, we would get C1H2, so we have CH2, and what is the molar mass of this guy? And so the molar mass of this guy is 112.1. So we just take 8 carbons plus 16 hydrogens. And so this just fills that in prettier form. Now, as we said, in a pure compound, it always consists of the same elements combined in the same proportions by weight. And we've done that looking at the law of definite proportions, okay, and the law of multiple proportions. So we're going to look at this percent by weight. And so we've seen this before. Here's ethanol, and we're looking at the percents by mass. Now, what we can do is we can look at the formula of a molecule and determine it in nature. And so if we look at that, if we can get our mouse down here.
What happens if you have something like this, and you want to find out if something like this is inside? Obviously, you can't tell just by looking at it, but if you separate things out, the answer becomes clear. Scientists have the same problem. How do you know if there was once water on Mars? Or, for that matter, life? Obviously, you can't tell just by looking at pictures of Mars, but scientists think the answer may lie hidden in tiny molecules in Martian soil. So, how do you take apart a molecule to see what's inside? Luckily, scientists have a tool to do just that. It's called a mass spectrometer, and it lets us take an extremely close look at whatever we're studying. And even though Mars immediately comes to mind, mass spectrometers are used in multiple NASA missions. They're also used in labs for hundreds of scientific purposes. But the important question is, how does it work? Today we'll be looking at a special kind of spectrometer called the quadrupole mass spectrometer. It's called this because of the 4 long poles that make up the center of the instrument. So say you have a sample that's been turned into a gas, and you want to find out if it contains certain things. The gas is sent into the mass spectrometer, first hitting a piece called the ion source. Here, a stream of electrons hits the molecule, breaking it into fragments and giving each fragment a charge. Next, the fragments enter what's called the analyzer. Here, they're separated based on their mass, and the analyzer is tuned so that only the fragments we want to see make it all the way through. Everything else flies off in a different direction. After this, the fragments hit what's called the detector, and scientists record the data. If you're looking for more than one kind, the analyzer can scan across a range of fragments, building up a record of not only what kind, but how many. Once you have these results, called a mass spectrum, you can verify that your sample in fact contains what you're looking for. And here, the real work begins. The mass spectrometer is a powerful tool, and by taking many samples, looking at the results, and studying what we find, scientists can work to discover not only the secrets of water and life on Mars, but also answers to bigger questions about the universe. And all by studying something as tiny as a molecule.
Okay, so let's go back here. Okay, so in this empirical formula, what we want to do is, first of all, let's look at a problem, and I'm going to lead you through the steps. In this kind of problem, we need to make some assumptions. So hopefully you're watching this video because you have a leg up on everybody else in the class then. So here we have a gaseous compound containing carbon and hydrogen was found to be consisting of 83.65% carbon by mass. Determine the empirical formula of the compound. So we know it's going to have carbon and hydrogen, and we want to find these ratios. The first thing you need to do is obtain the mass of each element present in grams. Now, the first assumption is that you have 100 grams of the compound, which makes your work really easy if you're given a mass percent, because right away you can write 83.65 grams of it is present in a 100 gram sample. Well, then all we have to do is find the other compound in this case, which is hydrogen. So we're going to take 100 minus that. And so we're going to see that present in this molecule is 16.35 grams of hydrogen. So this is our first assumption, very important. Then we're going to determine the number of moles. Now, as I said in chapter 2, if something is not in moles, get it in moles, okay? So at least you've done a step in a problem. So even if you don't know what you're doing, you can at least get something into moles. So if you know how many grams of carbon you have from chapter 2, we know how to get that into moles using the molar mass, which comes from the periodic table. Don't round off the molar mass. So it's 12.011 given the periodic table that we have for the exam. So you have how many moles of carbon you have. You do the identical thing for hydrogen. Okay? Now, once you have moles, now you can look at this mole-to-mole ratio, because the carbon and the hydrogen, these subscripts, are moles of how many carbon moles are there in the compound, how many hydrogen moles are there. So we need to get this simplest whole number ratio, and you're going to see these are not in whole numbers, and we're not going to, quote-unquote, round them off in this fashion. We need to get their mole ratio relative to one another. And so what we do next is we divide the number of moles of each element by the smallest number of moles present, okay? And so the 6.964 moles of carbon is the smallest number of moles. So if we're dividing that by 6.964, we're going to see that for every 1 mole of carbon, we're going to take the 16.22 moles of hydrogen and divide it by the 6.964, the smallest number of moles present. We'll see that we have 2.337 moles of hydrogen. Now, this is not close enough to 2 to round down. And so we'll look at the next step here. And a lot of people forget this next step. So if you have to get to a small whole number, we may need to use an integer to convert them to a small whole number. So if we were to take 2.33 and multiply it by 3, we're going to get basically 7. We're going to get 2.99. And so that is close enough, 6.99. And so that is close enough to round up to 7. Well, if we multiply hydrogen by 3, we need to multiply the number of moles of carbon by 3. So if you do one thing to one side of the equation in math, you got to do it to the other side. So our empirical formula will end up being then the whole number ratio of every 3 carbons to every 7 hydrogens. Now, someone may ask, well, how close do you have to be to round down? So let's say we had 2.1 moles of something. That's probably roughly 2 moles. Or if we had 1.99 of something, that's roughly 2 moles. Or what if you had 1.75 moles of something? Not close enough to round up. Do not say that's 2. You're going to have to multiply this at 1.75 by some whole number until we can reach a whole number for that. And so if you were to multiply this by 2, you'd get 3.5. But if you multiplied it by 4, okay, here, you're going to get 7. All right, so, that's what we're looking for. And so 2.1 can round down to 2. 1.9 can round up to 2. But like 1.75, 1.8, you can't round up to 2. And so by practicing at some of these problems, you're going to kind of see if you're able to round or not. So here, and this is analysis. So like, let's say we're taking chemistry 222. And in our case, it would be 162. If we were to look at this, and we have used some machines to determine a compound's percentage by mass, here again we have carbon and hydrogen. And they do that a lot with carbon-based compounds, organic compounds. And so we're going to assume 100 gram total again. So we have 92 grams of carbon and 7.74 grams of hydrogen. Just took our 100 minus that. So we're going to get them into moles, and we'll do the same thing for hydrogen. Now you'll notice that the same number, so we're going to divide by the 7.68, and we get approximately 1 mole then of carbon for every 1 mole of hydrogen. So our empirical formula is just CH, okay, 1 to 1. Now, it says if the molar mass was determined by a mass spectrometer, as we just saw in the video, to be 26, what is the molecular formula? So right now, if we were to take the mass of the empirical formula, it is 13.0189 grams per mole. The actual molecule in nature exists and has a mass of 26. The empirical formula has a mass of 13. So the molecule is 2 times as big. So we would take the empirical formula and multiply it by 2, And so in nature, the molecule's actual formula is C2H2 as it pops up on the screen. Now, the molecular formula is the exact formula of the molecules found in nature. And the molecular formula is always an integer multiple of the empirical formula, where n is this integer. Now, as we saw with our last problem, we determined with the C3H7, what is the molecular formula of the compound? We used a mass spectrometer and we found the entire molecule weighs 86.2 grams. So if we were to take the molar mass of the empirical formula, and this is the empirical formula. On the basement, upstairs is how much does the molecule actually weigh. If we were to take the mass of the molecule divided by the empirical formula, you'll see here that the actual molecule weighs 2 times as much. Okay, now we've had a couple examples here that there's 2 times as much. Sometimes it's 5 times as much, so just don't think it's always 2. And so 2 times the empirical formula will get us the actual molecular formula. So in nature, the molecule actually runs around as C6H14. Now, in 162, again, I did our loveliness here. We've changed our numbers here of classes. Here we've got boron and hydrogen. What is the molecular formula? So as you're going through, I'm just going to put all of the answers up here, because again, you will get everybody into grams, assuming 100 gram total. Get everybody into moles using the molar mass from the periodic table. Multiply by the smallest number of moles, so to get your mole-to-mole ratio. If you had 3 compounds, you would have to look at the 3 moles of things, you know, the different things, like let's say you have oxygen in here, and then look at the mole-to-mole ratios. So here it's 1 to 2.5. So we'll multiply the hydrogen by 2 to get it to be 5, which means we need to multiply the boron by 2, and our empirical formula is B2H5, simplest whole number ratio. Now, if the mass of the molecule, okay, was 53, the empirical molar mass, okay, is 26. And you'll see, oh man, she did it again, times 2. So the molecular formula is 2 times as big as the empirical formula. Now, I'm going to stop here because I want to give a separate section for looking at burning and by combustion, looking at chemical analysis, because it's another way to look at determining the empirical and molecular formulas, but it goes into a little bit more depth. So I'm going to continue with section 3.9 in the next video.